Welcome to the presentation of the project OpenModal. I'm happy I can introduce it here at the International Conference on Engineering Vibration. It is a project that actually started out of frustration when some of the guys that were working in the lab left to work in industry, and they were unable to actually implement all the ideas in their application. So I will now start and show you what was the frustration. So when you have, we researchers, we are always looking for great ideas. That is our job. We study other people's research. We do look for state-of-the-art and try always to find a good idea that is worth publishing. And that requires usually a lot of coding and also experimental work. And at the end, when you're happy with your research, what you do, you write a paper. Then, this paper, the final stage of your idea is actually the industrial implementation. But let me give you a few more details about from idea to implementation. Usually from the idea to paper, it is done at the universities, but the final implementation is usually in industry. And if you do open science, then your ideas are clearly exposed because you publish your code. Your paper is for sure public. It can be open access or not, but it is public. But your ideas are implemented usually by someone else who needs to see your idea, and it is implemented in commercial, closed software and closed hardware. So what is the problem? What is the frustration is that if you have great ideas, you can do all the work up to here, but someone else needs to see your idea and implement it. And that needs time. And besides that, when you leave a research institution and you have great ideas, you actually do not have an easy way to implement your ideas. Imagine this framework. You have your idea. You do open science. You publish the ideas. But you have an open software and open hardware framework where you would be able to directly implement your ideas into this framework. If you would have available that framework today, what you could expect? Because you would have a faster way to direct implementation, and the code and everything is public, you could expect that you would have greater scientific, faster scientific progress, greater scientific impact, and you actually have the possibility to have industrial implementation. And OpenModal is about creating such a framework. So we would like to create a framework with all the basic steps in experimental model analysis that is required. That means generation of the geometry, measurement, data acquisition support, identification methods, and also the animations. So let me give you a few more technical details. What we will show you later is built on top of open source Python scientific ecosystem. I'm quite sure that you are aware that Python has been increasing in popularity in last years, and there's a lot of people that do daily research and develop in Python today. What we are doing, we are right now developing on GitHub, which is a common framework for open source projects. For now, we have a closed community, but we are about to go open in 2016. It is developed by researchers from industries and universities. Our goal is to have a simple and intuitive application, and that means both for usage and also for development. And with that, I would like to go and show you the OpenModal in action. So this is the current state, how it is working. And with that, I will ask my friends Matthias, Blaž, and Micha to help me. So let's start. So what we will show you. We have here a simple beam. We will measure the frequency response functions at 10 points, impact excitation, a roving hammer, and yes, what you see here is you have 4 steps. So you need to define the geometry, measurement, analysis, and animation. And we will first start with geometry. What we need to define 10 points. Blaž is now putting data for the 10 points. For sure, you have all the modern user interface capabilities, like here, copy and paste. You can also import universal file format. And as the points are defined, you can see here that the view is updated. Now we will focus slightly to the defined geometry. You can now easily add, so we are now at adding nodes. Now Blaž will add lines, and then you can also continue with triangles. I said that we have import and export capabilities for the standard universal file format. Let's see now. Okay, then we will continue with the measurement. Okay. We will not show you triangles here, but if you would have like a surface or whatever, then you need to have the support for triangles, for complex geometries. And this is not the case here because we are showing you a simple case and how it is implemented, so the current state. So let's go now to measurement. Okay, we have here a window that I will explain later, but now we will go to measurement. We need to define the data acquisition system. What we are using here, we are using a National Instruments DACU system, which is very common in research and also industries all over the world. So what you need to define is here impact and response acceleration measurement, window length, zero padding, window parameters, averaging, trigger level, and also what Micha did here is already show like a test run. We are happy with the test run now in the frequency domain, and we will now continue with the measurement. As we have a roving hammer option, the geometry is directly linked to the measurement, and the reference nodes are appropriately corrected. So you see here the time domain impact. Here is a zoom of the time domain, so you can see if you have double hits. Here is the frequency domain of the impact hammer. You see the frequency response, and that is the acceleration time domain. Frequency response functions are shown here. You see that we are already at point number 6 out of 10. So you see everything is running quite smoothly. If we are happy with the measurement, we just accept it and we move then to the next point in the geometry. The next thing is, we now have the frequency response functions for 10 points. We can go now directly to animation, and we can show the deflection shapes directly without any model identification methods. So we are now showing here, you see the first natural frequency at roughly 317 Hertz. Okay, and you can directly out of frequency response function, you can show the deflection shapes. But the other way, typical in model analysis, is to go to the analysis. So we could now continue with the second natural frequency, but we are now going to the analysis, and we will use the least squares complex exponential method. We have here some options like sum of frequency response functions or complex mode shape indicator function here. And yes, with this least squares complex exponential method, we need to define the frequency range of interest. We will go here from 100 to 1 kilohertz. Then the next step is the stabilization diagram. Okay, what we need to select here are the stable poles. Stable poles have been selected, and next step is the reconstruction. And you can now see blue curve is the reconstructed frequency response function, and red is the regionally measured one. We see that we have a good reconstruction at all measurement locations. So we go back to animation, and now we can show the identified mode shapes. So that is now the identified mode shape, and the second identified mode shape. Okay, thank you, Blaž. We are now continuing with the presentation. So I will now sum up some of the capabilities. We have a complete support for universal file format with regards to geometry, measurement, and identification parameters. So everything can be imported or exported. As you saw before, the geometry is supported from nodes, lines, triangles. So what we have is we have experimental model analysis and operational model analysis, both impact and broadband excitation. And before that, I had here data acquisition. Data acquisition, currently we do support the National Instruments hardware, but more are about to come. It depends also from the interest that is from the users. And yes, for sure, we have animations support. Okay, so here we are at the core team. For now, this is a closed project which is about to be open in 2016. All the members come from the Laboratory for Dynamics of Machines and Structures, which is headed by Professor Bolteger, the head of this conference, or the chair of this conference. And yes, the team is Matthias Mörschnig. He is working on structural dynamics and vibration fatigue. He will finish his PhD in 2016. Miha Pirnat, he is the one that left the lab in 2013. He had great ideas, but was unable to implement them. He was working at that time on structural dynamics and noise problems. So there are some ideas how you can bring those both fields together. With regards to experimental model analysis. And Blaž starts. Blaž is working on substructuring methods. He is about to finish in 2017. Mattia Brumat is here. He is working on full field damping, direct damping identification methods. And Tadej Kranec, he finished his PhD in 2014, and he was working on strain experimental model analysis. So with this, we are close to the questions. And if you would like your ideas to have a fast track towards implementation, and you like what you have heard, we invite you to contact us and join the development or support us in any other way. Thank you very much. We are now open for questions, discussions, proposals. Yes, Tom.
Which MATLAB, or excuse me, Python GUI package were you using?
We are currently using PySite.
PySite?
Yes, PySite, which is a very good package for graphical user interface. But we are open to that. You know, if there's something better in the next few years, no problem with switching of that. The software is designed to be open and to be easily to be adopted for some changes that make sense and are reasonable.
I'm not familiar with PySite, but is that like, do you need a license?
No, it's similar than PyQt, but the license enables you to use it for whatever thing you would like to use it. So it's completely open.
And is it available on Windows and Linux?
Yes.
Okay.
Yep.
Thank you.
Okay. Some more questions, comments? Here, yeah. So the question is if we are using Python 2 or Python 3. We are using Python 3. You know, Python 3 is now all the major packages have been ported to Python 3 since like at least 1 year. And if there are any packages that have not been ported to Python 3, they are probably not in active development anymore. So we think Python 3 is the future, and we are looking into the future. So Python 3 only. Okay. If there are no, yeah, one more question, yeah?
I was surprised you didn't say that you use DataSoft or Deletron.
We are open to. So, you know, we are welcoming anybody. If you have an idea how to make it better, you know, contact us. Tom, Erwin, please.
Are you going to post a user manual and a theory manual, like PDF document?
Our goal is to have an, you know, intuitive application. You know, you need to have some background on the experimental model analysis. It's a dangerous tool to use if you don't know what you're doing. So that is the first rule, intuitive application. But sure, we will have the complete, you know, you have an open source project, so all the code is exposed. You know all the details, how it is actually done. So, and we will also have documentation, yeah, sure. But that is an open source project, so everything will be openly available, as it is usually is with open source projects. Okay. One more question.
There are some possibilities to average spectra
Yes.
and to visualize coherence functions.
Sure, yeah. Yep. So, you know, we have not shown that, but for sure, you know, you need averaging, you need, as I said, windowing, etc. That impact excitation here is very simple. You know, it's not really required that you would.
For the demonstration of
Yes, 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 yes.
It was not demonstration of all the functions.
Not at all. You know, we have not shown, for example, the operational model analysis. We do support it, and with operational model analysis, if you do not have averaging, you know, you will not come far. Another question here.
Do you have any roadmap of development for the capabilities that you intend to implement?
I'm not sure I get you.
Yeah, if you have any roadmap.
Roadmap. Yeah. If we have a roadmap. We have a roadmap, yeah, and we are working on that, but for now we are closed. You know, before we are not sure enough, you know, that we are ready and we have enough, we are not going public. As you saw today, the application is working, it is safe, it is quite polished, but we would like to have it to be sure when we are going public that everything is fixed. And why we do have this public presentation here is that if there is interest, we would like to gather it to get for the alpha testers, etc., etc. So we would like to have feedback from the users, and we are already gathering so like invitations. So we have an invitation, you know, at the web page. You can easily contact us if you have ideas how you would like to make it better, or you have, I don't know, a proposal, or you know, to include that hardware, or you're already working on a new method for the model identification or whatever. You know, we are happy to start working on that. This should be a framework where you researchers and we would be able to do research that has greater impact and is faster. So that is with regards to the research community.
And my second question is, are you intending to stay on the model identification? Or
No. That is OpenModal project, and we see it slightly broader than just experimental model analysis. That's why we don't say always, you know, experimental model analysis software, because there are ideas how you can implement, for example, boundary elements, finite boundary elements, and on top of the experimental model analysis, you can simulate noise, or you can also include some high-speed cameras for model analysis or whatever. I don't know what are the bright ideas that the scientific community is working on, but we are open to that. And if you have a commercial software, you know, they need to see your idea and they need to see it as significant enough to include it. But you are open to work on your own branch of that software and use it just for you, but you have to have the same license that we have it. So if we are developing openly, also everybody who is using that source, their work needs to be openly available. That is so we do think that in that way we are speeding up the progress and the scientific value of the contributors. Tom Irwin, yes?
Have you tested the software on maybe a structure with a high modal density where you have closely spaced modes to see if it can resolve the frequencies and damping for like closely spaced modes?
That was not the focus right now, but we are supporting all the best methods, also the polyreference method. So that is just depends from the method that you are using. So that's something that we have not been focused right now. We are creating the framework. I'm happy. Quite a lot of detailed and interesting questions, but if there are no more questions, then I would close that presentation, and thank you everybody for attending it. Thank you.